All right, part one of the periodic table. Are you ready? Let's go. In class, you're going to choose your participation method. So the modern periodic table is arranged by what? Atomic number. You got it. And that's evidence of the periodic law. So when elements are arranged in order by their atomic number, their properties repeat periodically. And they end up in groups. And here's a little way to remember group versus period. Notice period at the end of the sentence. All right, properties of elements repeat because of valence electrons. Valence electrons that are unpaired are going to bond, and valence electrons determine chemical reactivity as well as chemical properties. So 8 valence electrons is an octet. An octet of valence electrons is stable because each of those valence electrons is going to be paired up. Where on the periodic table do we find elements with a stable octet? Yeah, group 18, the noble gases. But what element is an exception? It's stable but does not have an octet. You know it, it's helium. So if an atom does not have a stable octet, it is going to react. It is going to bond to make that stable octet. Now we're going to learn more about bonding in a later unit. For now, what is important to understand is that elements will make an octet in the easiest way possible. So is it easier to give up electrons to get the octet, or is it easier to accept electrons to get the octet? Take the easy way. So only valence electrons, though, are going to be gained or lost. The nucleons, the protons and the neutrons inside the nucleus, stay in the nucleus. They're not lost, they're not gained during the bonding process. So atoms are going to lose or gain valence electrons to make an octet. But if you remember from before, atoms were neutral because they had the same number of protons with a positive charge and electrons with a negative charge. So they balanced and were neutral. But if they're losing electrons and the number of protons doesn't change, that means they're going to end up with a charge. So if they're gaining or losing electrons, but protons are staying the same, they're going to end up with a charge. And we call this charge the oxidation state. Now you're going to have to be able to do some simple math to figure it out. Like this. What's the answer to this? -3. What's the answer to this? 0. What's the answer to this? +2. So that's basically the kind of math you're going to have to do for this. So a sodium ion. So if you look at this picture right here, you can see that it says it is losing an electron. So you can see right here, an electron is lost, right? As it loses the electron, look at what happens. It loses this third energy level. But now if we look here, 2, 4, 6, 8. Oh my goodness, now it has 8 valence electrons. Well, that's why it did it. Why didn't it gain? Well, because it only had 1 valence electrons. So if it had to gain, it would have had to gain 7. That's a lot harder, okay? So when we think about the charge, it still has those 11 protons in the nucleus, but now it does not have 11 electrons. It only has 10 electrons because it lost one. So if I have 11 positives and 10 negatives, I end up with a +1 charge. Now, if you look here on the periodic table, it tells you that. That's the oxidation state for sodium. So what that means is, in order to get a stable octet, sodium will lose 1 electron. If you look at electron configuration, it makes sense. Look at this. There's valence electrons. It loses that 1. It's left with this electron configuration, which has 8 valence electrons. Ta-da! So how do you think this atom will make a stable octet? So look in the outermost layer. How many valence electrons do you see? What would make sense? Well, it would make sense that it's going to lose one. And what's the charge of a potassium ion? So the atom lost one valence electron. If you look here, it'll tell you the answer, but it's +1. How do you think this atom will make a stable octet? So look at the outermost shell. How many valence electrons does it have? So what would make sense? It's going to gain one. So what would the charge of the chloride ion be? Now notice I didn't say chlorine ion. We'll learn more about this later, but nonmetals, we have to change to ID. But if you look right here, it has a big list. Also makes most nonmetals a little bit more confusing. But for now, we're just going to look at the top one. Make it easy. So what is the charge? -1. Why? Because it has one more electron than protons. How do you think this one will make a stable octet? Look at the outermost shell and make a guess. What do you think will happen? Well, it'll lose 2 valence electrons. So we're talking about, see how it says 20 protons? We're talking about calcium. And look here. What's the charge of that calcium ion? Well, +2. The answer's on the periodic table. How do you think this one will form a stable octet? Look in the outermost energy level. Look at the outermost shell, the valence electrons. Well, it'll gain 2 electrons. Why? Well, because it had 6. Otherwise, it has to lose 6. Gaining 2 is a lot easier. And what's the charge of a selenide? Remember, this is a nonmetal, so we got to make it ide. We'll learn more about that later. And for now, on the nonmetal side, we're just looking at the top one. So it's going to be -2. Now, don't forget the helium exception. It is stable with 2 total electrons, not 2 valence, although yes, it does have 2 valence. The reason it's stable is because it has 2 total, okay? So stable is an octet or 2 total electrons. So how would this atom make a stable octet? Well, we look at the outermost energy level, and I see 1 valence electron. So it makes sense for it to lose it, right? But I have to check and see what's underneath. But now it doesn't have 8, but it has 2 total. So it is going to lose that valence electron. What is the charge of a lithium ion? So do you see right here? +1. So what happens is it loses this 1 valence electron. So what's left? Yes, 2. But the important piece is 2 total. That's it. There's nothing else. So how would this atom make a stable octet? Again, we look at the outermost energy level, and it's going to lose 2. So it's 4 protons. That means it's right here. It's beryllium. What is its charge going to end up being? Well, +2. Now, why is that stable? Well, because it lost these. All that's left is 2 total, just like helium. Now, we talked about these before, the main group elements, like the tall ones. Those are the representative elements. They have consistent patterns of valence electrons, consistent patterns of similar properties. Okay, so this is the S block, this is the P block over here. Those are the ones that contain our representative or main group elements. And down each group, they have the same number of valence electrons. Now, groups are also called families, so sometimes you'll see that terminology. So first one, alkali metals, group 1. They're obviously metals. They're soft, so you can actually like cut them with a butter knife, okay? They contain 1 valence electron. Because of that, they're extremely reactive. They will very quickly lose that 1 valence electron. So they are the most reactive metals. so reactive, in fact, that we don't really find them as pure elements in nature. So here's an example with lithium. You can see you can cut it with very easily with a knife. You can see that it is shiny like metals, okay? So here they are, the alkali metals in group 1. Notice hydrogen right here. Not an alkali metal. It's in its own little, that's why it's stuck off the periodic table a little bit. It's not an alkali metal. So alkali metals, remember, very reactive. They will react with water to make alkaline or basic solutions. When we ship them, we do actually have to store them in oil so they don't react with oxygen or water vapor in the air. They're never found as pure elements in nature. So here's rubidium, a little bit of rubidium in some water, explosive. Here you can see the reactivity increases as you go down the group. So you can see the amount of reaction you get when you put a piece of lithium versus a piece of sodium versus a piece of potassium. So rubidium, like you can see in the GIF, has even more reactivity. Cesium would be more, and francium would be the most. Okay. Here you can see them stored in oil because it is too dangerous. They will react with the air, oxygen, or water vapor. Alkaline earth metals. Well, that's group 2. They're also metals, but they're a little bit harder. They have 2 valence electrons. So they are highly reactive. They lose those 2 valence electrons. They're just not as reactive as alkali metals. So they all have 2, and their reactivity still is going to increase going down that group, but just not going to be as active or reactive as the alkali metals. So here you can see them in group 2. Now, the alkaline earth metals, again, highly reactive. They still react with water to make alkaline or basic solutions. They're usually not found as pure elements, but they can be. Here you can see this is burning a piece of magnesium ribbon. This may be something that you do in lab later on. Halogens, group 17, nonmetals. They have 7 valence electrons, group 17, 7. They're highly reactive. So instead of losing a valence electron, they're going to gain one. So they have 7. All they need to do is gain one to make 8. They're the most reactive nonmetals. They like to pair up with the alkali metals because alkali metals like to give up one, halogens get one, perfect partners. Okay, so you can see 7 valence electrons. Here we go, group 17. Now, the halogens have a wide range of physical properties. So the top 2 elements, fluorine and chlorine, are gases. Bromine next is a liquid. And iodine and astatine below that are solids. So it's the only group on the periodic table where you're going to see elements in every single state of matter at room temperature. Now, halogens and alkali metals, like I said, they're perfect partners. Alkali metals are giving up an electron. Halogens are trying to get one. Perfect partners. Now, noble gases. That's group 18, very stable. They already have 8 valence electrons. They have very low reactivity. Why? Because they already have those valence electrons. But you're not going to forget about helium, right? So helium is still stable, but it's exception to the octet. Instead of having 8 valence electrons, it has 2 total. Now, the noble gases on the periodic table, you can see right here, group 18. What else? Very low reactivity. So we utilize those things to our benefit. Helium is used to fill blimps, so it has a low density, but it's also not flammable. Neon has uses like in lighting, in TV sets, in lasers, freezing corpses. Helium, neon, okay? Very important. And that low reactivity gives them usefulness. Then we have hydrogen. So hydrogen, well, it's kind of an oddball. So first of all, it's the most common element in the universe. 3 out of every 4 atoms in the entire universe is hydrogen. It has 1 proton, 1 electron, and that gives it some very unique properties. So it's up here on the periodic table. Kind of set off, it's its own thing. It's not in group 1. It's just in a class all by itself. So it can react with a lot of elements. In fact, it can act like one that likes to lose or one that likes to gain electrons. It's flammable. It reacts with oxygen to make water. It's a component of organic compounds. I'm going to do a whole unit on organic compounds. I took multiple courses on organic compounds. So here you can see the explosive nature of hydrogen, and here you can see it combines with oxygen to make water. In the next lesson, we're even going to look at more, so let's look at some review questions. Which element is in a class by itself? Hydrogen. Which group of elements has 2 valence electrons? The alkaline earth metals. Which group of elements contains the most reactive metals? Alkaline metals. Which group of elements contains the most reactive nonmetals? Halogens. Which group of elements contains the least reactive elements? Noble gases. Okay, in class we're going to be completing an exit ticket to see how much you understand, and hopefully you have a better grasp of the periodic table.